Welcome back. We want to talk about the pins right here, on this side. The pins on the microchip have a behavior that we can program to make them as if they're kind of like a battery. They can be positive or ground, right? In that case, they're called digital outputs. So I've got an example here where I've connected a red LED to a single pin. So I get a single pin and the LED is going to ground. And that digital output is turned high, so the red LED is on. For the two-way LED, I've actually connected it to two pins. And I've actually just used two resistors, so it's not too bright. And you can see with two pins, I can make the two-way LED switch colors. What I have, you remember with the two-way LED, when current goes one way, it's one color. When current goes the other, it's the other color. In this particular setup, I make one of the pins high and the other low for a short amount of time. Current goes one way. Then I switch so that the other pin is high and the first pin is low. And then the current flows the other way and we get the different color. So we're going to learn about the pins and how we talk about these pins and how we make them a digital output and turn them on and turn that off. So let's have a look at the pinout diagram. Now, most of the pins on our PIC actually do allow for digital output. Generally, it's digital input and output, but we're only looking at lighting up LEDs, so we're just talking about digital output right now. All the pins have multiple uses. That's called multiplexing. But we can pick which one of these features that it uses. For instance, RA0 is a digital output, or it can be an analog input pin. The way we configure the pins says which property it has. Now, if you wanted to know which pins are digital input-output pins, all you need to look for is the letter R followed by a letter and a number. So if it's, for instance, this one right here, which I just blocked by accident, right? If I block that out, RE3, that's a digital input. RA0, RA1, RA2, RA3, RA4, RA5, that's interesting. RA7 is before RA6, RC0, 1, 2, 3, over here 4, 5, 6, 7, then RB0 up through RB7. They're all digital input pins. This RE1, we're never going to use that guy. We use that for programming the computer chip, so it's spoken for already. Don't ever try to use that one. VSS is ground, VDD is connected to power. So most of the pins here are digital outputs. Now if I want to connect an LED to this pin right here, all I have to do is notice that pin 15, the pin I want to use, is called RC4. And we'll see the code we need to use to do that a little later. But there's one more thing that I wanted to mention, and that's safety considerations. Here's a simple circuit of the sort we've talked about in class. This would be the pin, right? And we're connecting a resistor between a pin that's set to high and ground. We know that the current through this resistor is given by Ohm's law. The voltage drop here is 3.3 to 0, so the voltage drop over the resistor is 3.3 volts, right? The current and the resistance, so we know this, we could look from the color code what the resistance is, and we know what current we have. But it's important to know one fact about our microchips. They only have a maximum current that they can output. It's about 20-25 milliamps. And if you try and draw more current out of a pin, you can actually damage your microchip. So if you actually want a current going through this resistor here, you need to make sure that the resistance is such that the current doesn't exceed this 20 milliamps. We can use Ohm's law, right, to find that resistance. So rearranging the Ohm's law equation to delta V over I, 20 milliamps maximum, 3.3 volts, 165 ohms is a safe resistor to put in this circuit. Anything smaller will probably draw too much current, and your computer chip and your circuits can start giving odd results. You can even cause problems, overheating in your chip and the like. You could destroy your chip. So you always want a resistor which is keeping the currents from the chip, or keeping the currents that come out of the chip, fairly low. Now we're trying to make LED circuits. So an LED circuit looks more like this, right? You'll have the pin over here, you'll have a resistor, and a late emitting diode in series. This is the symbol, of course, for a late emitting diode. And I should have mentioned that this is the symbol for ground, and this is the symbol for a resistor. Now in this case, things are a little bit different. LEDs don't have a big resistance, but they're not like resistors. One of the things about these guys is that if you're operating them correctly, there's always a 2-volt drop over the LED. It's called the forward voltage, right? As long as that voltage is 2 volts, you're going to get it to light up. Okay, so we're interested in how much current we draw from the pin. We can still use Ohm's law, but now you have to realize that if this is 2 volts here, and we started with 3.3, then the voltage drop between the power pin and the LED, this is only going to be 3.3 minus 2 volts, or 1.3 volts. So the maximum current that we can get out, this now works that this resistor could be smaller than it was in the previous case, down around 65 ohms. We don't need to use a 65 ohm resistor. If we have a 200 ohm resistor, that's fine. You'll remember that the bigger the current through the LED, the brighter it will be. So you can control the brightness of the LED by what kind of resistor you have in. But most of you have noticed that the LEDs are pretty bright with a 200 ohm resistor, so we're not worried about that. So now let's look at the basic code for simply turning an LED on, and it's here. I've got some comments here. Right? The first thing is we need to include this library, xc.h, anytime you want to use the features of your computer chip. This is it. Okay? Also, there's this configuration bits.h file that controls some of the settings. Without this, you might not get those pins to do what you want. Now there's a couple of commands for turning on the pins. Okay, it's this comment right here. This one, it says tris x bits.rxn. Well, X stands for one of the letters we saw. You might remember we had pins that had an A, a C, or a B in them. Right? So X could be A or B or C. Right? And the N, of course, stands for 0 through 7. Okay? So this command here configures pin RXN as an output. This is not a function as such. It's something called a special function register, also known as an SFR. It's actually a part of memory, and you're setting a bit in memory that makes this pin behave this way. We can treat it like a function, right? So equal to 0 means I'm making it an output. Okay, so now the pin's an output. Doesn't mean it's turned on. We've just configured it to behave properly. So this is a configuration command. If I want to turn it on, it's right here, right? Port xbits.rxn equals 1, okay? This turns the pin voltage on, whatever RXN was. You'll recall we wanted RC4 to turn on pin 15, so we'd be using C4. So for me to turn pin 15 on, I just come down here. It was a C pin, and it was C4. Configures RC4 pin 15 as digital output. Okay? And if I want to turn it on, it's port, capital letters, P-O-R-T, C, lowercase bits, dot RC4 equal to 1. Okay. Turn output to 3.3 volts. Now it's turned on, so when this is loaded on a chip, if I've got my LED connected to this pin, it'll turn on. It's that simple. If I want to turn it off, I just make it 0, just like that. So now the pin acts as a ground, right? So the first comment here turns it on, and then this turns it off. This is not especially useful because it turns the pin on, so the light comes on, but almost immediately, and I mean almost immediately, we're talking about microseconds, we turn it off. So that's not so great. You could do something like take this code and put it inside our while one forever loop, right? The while one loop keeps repeating over and over. So this is turning the pin on, turning the pin off, turning the pin on, turning the pin off. So again, it's going to be turning on really fast and off really fast. So you won't really notice it as something flashing on and off. What you'll notice, in fact, is that it's not going to be as bright. Like if you look at the overhead lights, they actually come on 60 times a second. They're on and off, but they appear continuous to us. So the LED is on half the time, so it's only about half as bright as it would be otherwise. Okay, so we've seen how to turn on and turn off or even flash an LED, but we also have these two-color or two-way LEDs. Now for that, you're going to use 2 pins. That gives you control over the direction of the current, and therefore direction, not the direction, but which color the LED shows. So here we have us turning on the pin RC4. Well, the other pin we would use can be any pin whatsoever, but for convenience, I'm just going to use the pin next to it, RC5. they're both configured as outputs, meaning I can make them high or low, high or ground. So in this case, RC4 is on. If I make this RC5 like this, nothing will happen because both pins are high. So I need to turn one of them off. That didn't work very well. Right? So I turn this to 0, right? So the current will go from high, which is RC4, to low, which is RC5, and that'll turn your two-way LED one color. And if I switch them, I switch which one is high and which was low. So now this is 0, and this is high. Oops. This is 3.3. The other direction, the other color will show. Okay? So we can make it any color we want. Usually, and we'll show this a little later, you're going to want the LED to be either red or green, for instance, as a stop-go. Now, of course, another thing you can do is you can take this right here and put it in the while loop, as we did before with the single LED. Right? And so this turns it one color, and what we're going to do, right, we're going to flip it, change the polarity. Right? Okay. And so this will be, say, red, and then green. And it'll go red, green, red, green, red, green, red, green, red, green, red, green, red, green. Many times a second. The speed of your computer chip is 1 megahertz. And these statements are happening roughly that fast, on the order of microseconds. So on for roughly a microsecond, off for a few microseconds, on, off, on, off, on, off. Your LED is not going to look like green, then red, then green, then red, then green. It's flashing so fast that your eye will see something amberish, yellowish, or green. Right? So with this red-green LED, you can have red, green, or amber. You could make a sort of traffic light with this. So we can use this setup, turning one polarity to make one color, and then another polarity for another color, to flash LEDs on and off, but it's too fast. What we'd like is some control over how fast or how long it's staying green and how long it's staying red. That turns out to be fairly simple. In the XC library, there are what are called delay functions. All that happens is the processor waits and does nothing for ever much time you want to wait. So if we could put in something here like delay half a second, down here delay half a second, we would be able to see it turn on and turn off, turn on, turn off, turn on, turn off, much more noticeably. So let's take a moment to discuss some of these delay functions. To use the delay functions, there's a number of things that you need to know. First of all, our PIC runs at 1 megahertz. There's a time unit that's used in all the reference books for the microchip, and it's called the instruction cycle. That's the minimum time for an operation, like turning the pin on and off. That'll take one instruction cycle. More complicated instructions take more time to do and could take thousands or tens of thousands of instruction cycles. You can figure out how much time an instruction cycle is in real time by multiplying 4 and dividing it by the operating frequency, which is 1 million hertz. Right? Hertz is inverse seconds. So when you do this calculation, one instruction cycle is 4 microseconds. 4 microseconds is very, very short amount of time. Now the delay functions, there's 3 of them. There's actually a couple more, but slightly different delay functions. There's something called the NOP, so NOP bracket bracket, would give you an exactly 1 instruction cycle delay. Often not much use to it, but sometimes we put this into code to have a breakpoint. The one that's most useful to you is probably this next one, underscore delay, and the variable it takes is long cycles. The cycles cannot exceed 179,200. You might want to figure out how much time delay that is then. And the other one is delay underscore delay 3, where it takes a character. Okay, so this is going to 3 times, however, whatever the unit is that you're asking for, times TCY. Unit can only be between 0 and 255. So 3 times 255 is only 765. And so that's, yeah, that's about right. Instruction cycle. So it's not a long time. Here's some examples. If I ask for delay 100,000, then 100,000 time instruction cycles are 4 microseconds. That's 0.4 seconds. Now, you'll remember, this cannot exceed 179,200. If you wanted a 5-second delay, you could just call this function many times. Here's delay 3 times 100, so 3 times 100 times 4 microseconds. So we can use this in our program, say, to get a noticeable delay. So let me copy this. Let me go back here, right? Semicolon. Make that a lowercase l, right? And understand something along those lines. And v semicolon. And now it'll be, say, red for 0.4 seconds, green for 0.4 seconds, and we'll see it blinking on and off continuously. You should try this code on your own chip and make sure that it works. Remember that you're including this guy in your project. There are some other delays that we should talk about too. Okay, these delays underscore these guys are actually double underscore delay microseconds, float x, and underscore delays underscore milliseconds. They'll give you delays in times that are more familiar, milliseconds or microseconds to you, but they only work if at the top of the program you've defined this, that the crystal frequency is 1 megahertz. If your chip's not operating at 1 megahertz, say it was 10 megahertz, we'd add an extra 0 here. Okay? So if you want 1,000 microseconds, just plug in 1,000 here. If you want 1,000 milliseconds, plug it in here. Well, you have to be careful about that. X cannot give you a time less than 1 instruction cycle, or a time greater than 179200 instruction cycles. You should figure out how many seconds, or a fraction of a second, that this is. Okay? So now that we've finished, our code lets us turn pins on and off. We have control for how long they turn on and turn off, so we can make them blink in patterns, right? We can do all sorts of fun things. That's it for now.